Hey, so I'm George. My day job is WebGL graphics programmer, and yeah, sort of in the evenings and weekends I fiddle around with Haxe and sort of try and work out how I could have done my job better using it. It's normally sort of quite good to sort of release frustration with sort of other tech stacks that I work with professionally by sort of recreating some of the things in Haxe. So this is going to be quite a sort of bird's eye view look at some of the features Haxe provides to make writing performance code a little easier. So the sort of a lot of games you'll write don't necessarily need to take advantage of these features. But if you're writing something that's very physics heavy or VR where the frame rate sort of has to be sort of 90 hertz and sort of obscene resolutions, then this sort of stuff will become important. So in programming languages, there's sort of common trilemma where sort of you can categorize programming languages as portable, easy and fast, and some are a bit both, but very few or none are sort of near the middle. So sort of Python and JavaScript would be your easy and portable languages, and then maybe your sort of fast and portable but not easy languages would be C and C++. And then you've got sort of the easy and fast languages like Fortran and Julia. I think Haxe gets closer to the middle than most, and I'll go over some of the reasons why I think that's the case. I mean, why does this issue exist in the first place? Why is it so hard to write an easy, portable, fast language? And I think if something is going to be portable, it's going to be hard to take advantage of the sort of platform-specific features. So CPUs these days have specialized instructions that enable sort of fast math or various things. But if it's easy to write, you can't really be worrying about how it's going to be implemented in the hardware. You just want to be thinking about sort of your algorithm or whatever problem you're trying to solve. So So it's hard to hit all three. So Haxe has a few sort of special tricks. It's got in order of its power. So like it's inline constructors, abstracts, type-ordered macros, and sort of platform-specific magic. So abstracts can let you build advanced compile-time interfaces over things. Type-ordered macros can let you sort of rewrite sort of parts of the language or extend parts of the language as you like. And platform-specific magic is going to let you, only when you want to, take advantage of some special platform feature. All right, so one weird trick to reduce your garbage collecting stalls is the inline keyword. So you normally a vector class, I look something like this, regular sort of structure. You have fields for your elements and a sort of bunch of methods. So this might, I mean, it's a perfectly fine way of writing a vector, but it might not be as fast as you want, especially if you're using sort of creating and destroying hundreds of these, or thousands, tens of thousands of frame. Each one creates little objects and it gets registered in the garbage collector. And so every now and again, the garbage collector will sort of have to churn through all of them, and then you potentially sort of stall while it's doing that. So there's a little trick if you add the inline keyword to all your methods, including the constructor, which is unusual. You can get something. It can compile out without creating an object. So making a vector and the Haxe compiler along with a bunch of other bits and bobs produce something that just the vector fields and there's sort of the length functions. But not 100% reliable. It's a suggestion to the compiler. It doesn't instruct it, so it won't fail if it can't inline. So if you had your vector passed to some other to some function that isn't inlined, it's gonna break that optimization, and it outputs pretty much the same thing you put in. So yeah, if you want to write really fast vector class, it's not the best choice to rely on inlines. So next up, abstracts. So yeah, the abstracts let you define an interface over another type. Sometimes you want to be able to do this to sort of, depending on sort of maybe an API you're targeting. So if you're targeting WebGL, you might want to have your vectors based on typed arrays. If you do that, you don't have to worry about sort of data conversions all the time. So if you've got sort of meshes with millions of vertices, it'd be great if you could just keep everything in typed arrays and not sort of move back and forth, because that could be quite expensive. It can also make sort of fast but cumbersome types easy to use. So some things will come across are super efficient, and they're the best choice if you want to make something really fast, but they're a pain to use because it's a fiddle. And for example, if you were to write a vector using typed arrays, and like directly, so if you want to set the y property, you have to set the second in the index. So that would be an example of something that would be cumbersome. But you'd like to. So you can make an abstract over a typed array, and also pop in the inlines everywhere. So you define your public interface and your methods as you would like a regular class, except to sort of use something kind of unusual. And then in your abstract, you set this equal. So you sort of the sort of internal implementation is hidden from the kind of user of the vector. So when you set the x field, it's going to set the first element in the array. When you set the y field, second, and so on. And you can make this arbitrarily complex, and, but that should give you a rough idea of the concept. The more important thing is it's a zero cost abstraction. Because these inlines, it means it won't have any existence in your code base, just because the compile time. So it's a nice way to sort of make something kind of easy and pretty. Must not be. So if we have our vector like before, we set the fields. This compiles as sort of your array object and sort of the direct array access. So it can be really helpful. Sort of JavaScript is usually pretty good these days at doing all this automatically, but not always, and potentially not if you're compiling some of the other targets. So it's worth thing. Another example of good use of abstract is the enum flags type that's built part of the standard library. So sometimes you want to be able to store bit flags in an integer, and the reason is you can sort of pass a whole bunch of information in a sort of small packet that's easy to move around. So maybe a bit flag has the key that's pressed down on the keyboard. This keyboard's a very small keyboard and 3 keys, but if you did something like this in C, it would look like this. You do it with sort of bitwise operations, and you're not really interested in bitwise operations. You're interested in registering what keys press down. So this is kind of hard to read and hard to write. In a flag, sort of you can recreate this kind of with an abstract, and so you do the equivalent. This code sort of with modification compiles down into this. So that's the key advantage of abstracting. So the next more powerful tool is type building macros, and we're not going to look at sort of they're covered in other talks and covered on the internet. So we're just going to look at sort of generic macros or generic build macros. So they're among the most powerful tools Haxe has, because you can sort of rewrite the classes or types kind of arbitrarily. It's kind of not that far away from just pure sort of string wrangling. You know, sort of if you were to take a bunch of code and just sort of modify it on a sort of string-like basis, it's more advanced because it's done at sort of the level of the syntax tree. But it's much easier than working with the strings directly. But in principle, it's not that far from. With great power comes great responsibility. It's not. If you've not worked with TypedArrays and SIMD before, it's not obvious why you'd want to do it. Why would you want to be able to build a type at compile time? But once you get your head around them, your co-workers will sort of be will be trying to stop you from using them all the time, because it's a change of perspective on things a wee bit. So you want to avoid using them too much, because if they sort of overused, it can make your code base hard to read and sort of hard to follow. Because if you're changing some of the core behaviors of the library, of the languages, say, it's kind of not obvious, what it's going to do, and it gets kind of confusing. So yeah, you use them carefully, but when they're the right tool, they solve a lot of problems. So here's a simple example of the generic build macro. So the common example we had at work recently was we wanted a set of configuration that's strictly typed. So we don't want to make these optionals, because we want to be sure there's always going to be a sky color and there's graphs going to be supplied. All the fields should be supplied. And so we don't want to be checking for null all over the place. But we want a user of our library to be able to pass them without passing all of them together. So you can build you can create a macro that lets you add optionals to this automatically. So that's what partial is doing. It's going through and it's adding the optional keyword, optional metadata to each field. So the user doesn't have to pass everything through, but your library doesn't have to keep checking, and can be confident that they're all there. I won't go through this in too much either, because it's hard to kind of follow code on a slide. But the general idea is we're getting the type parameter from the type definition. So the type parameter there is options. So we're extracting that, following it just in case it's pointing somewhere else, maybe it's a type alias or something. And we're getting, once we've extracted the type and we know it's an anonymous field, we can go ahead and just push the optional metadata through and then return the new type with those new optional fields. It's quite easy to do. And in TypeScript, you've got partials, and you've got a similar sort of thing for picking certain fields. So if you want to pick just a few, cool. So going back to the vector, writing a sort of fast linear algebra library. How can we use genericMacros to make things better? So the ideal linear algebra library is going to be as natural as possible. We want to make it easy to translate mathematical notation to implementation. So if you've got sort of an implementation for frustrant fitting or something, it should be easy to convert that into code. And we want to make it as efficient as possible, take its maximum advantage of the machine it's running on. If it has special CPU instructions available to it, it should use those to make it faster. And we also want to make it easy to understand and maintain, of course. So we can use our generic build to extract, let's take a step back. We can make our vector class non-specific in length. So we can have we can define things. I mean, in the ideal case, we define things like a vector would just cover all the vectors. It would cover vector 1, vector 2, vector 3 up to infinity. And you define things like how vectors should be added. You add the fields one by one. And a bunch of operations, how vectors interact with matrices and whatnot. But you wouldn't actually have to go through and have a unique class for every vector. A vector 3 is the same as a vector 2, except for it just has an extra few lines, for example. So you kind of want to be able to define things in sort of pure terms, and generic builds can help us do that. So we can add, we can add the const metadata when we create our, when we define our vector class, and that lets us use constants. It could be strings, but we want to make sure it's numbers. So in example usage, you can define vector length of 5 elements, vector of 2 elements. If we define everything right, it'll error out. We try and operate, in incompatible vectors and whatnot. And it should automatically generate all the code to enable that. So this is a snippet from something, an example of an implementation that, like the vector 2, uses typed arrays behind the scenes. And we can, once we've extracted the length of the vector from the type parameter, we can use the sort of macro syntax to build a new type. Again, this is using the macro syntax to go ahead and what it's doing is, the macro syntax is a bit hard to read, but what it's doing is it's running through a for loop which generates a new line for each one. So, for example, in the add operation, we're generating a line that says, take the parameters, add them together. So you end up with sort of if it's vector 3, you end up with three lines for the add. It's ugly, but it's kind of nice. It's also you can specialize this for behavior with matrices and whatnot. It'll fail if you try and use something that's not the type we're creating. So the add is defined in terms of if n is 3, this we generated with vec 3, vec 3. So you can't add a vec 2 and a vec 3. You can add vec 3, for example. So it's a simple example, but you can probably imagine how this could become quite advanced, and you can sort of do things with it. All right, so the next thing to talk about is SIMD operations. So the idea behind these is you can parallelize code that looks like this. Code where you've got this sort of where you have an operation or sequential operations that are independent of one another, and they're supercomputing and whatnot. But most CPUs have a lot of bandwidth for these operations. So by parallelizing, I mean you can take all these operations and do them in one go. As long as they conform to a certain situation, the CPU has the capacity to do that. And it'd be great if we could do that in Haxe, if we could just use these magic instructions, because you could get sort of pretty much a 4x speed up from that, and more, because some of these operations can do sort of many more lines in one go. I mean, there's a limit depending on the CPU you're using, but the sort of new CPUs today have I think 512 bits that can be processed in one go. So that's a lot of operations if they were handled sequentially. So it's an example of using SIMD operations. You get even bigger speed up if using multiple threads, because it's multiplicative. Like each thread runs its own SIMD operations. So in this example, the person's getting sort of 3x speed up on their Mandelbrot simulation, and 17x speed up when they're doing 8-threaded SIMD operations. It's a huge deal if your math library is taking up a big chunk of your frame time. It could cut it down by quite a few milliseconds, which is a lot when you consider you might only have 10. If you're running for targeting VR. So, why do I have to care about SIMD operations? You know, I mean, compilers are smart. Can't let compiler do it? And unfortunately, there's a good reason why they can't. Or they can't do it easily. They can, but just the things have to be sort of just right for them to be able to do it. And it's because C and C++ and many other languages are sort of so flexible that we can't be sure if in this example that B is pointing to the same memory as C, for example, because the nature of SIMD is we have to separate, everything has to be separate. So there's two ways to get around this. We have to do it manually, where we actually essentially call the specific instructions by hand, which is a pain because different CPUs, AMDs have different instructions for Intels, have different instructions from older Intels and so on. So it's not ideal to do it manually. But that is the common way most people do it manually, it seems. And that's just historical because previously compilers couldn't really do it themselves. But in 2016, they can. So we want to be able to make sure if we're targeting C and C++, we can get our code to generate in such a way that it can parallelize or generate these what's called vectorizing. It can vectorize these operations. So the tool we have is C++ platform-specific magic. So by default, if you wrote a for loop, or if you wrote, if you generate this code with a for loop, it wouldn't easily vectorize. So this is down to the way sort of HTTP. As great as it is, it does lots of things to make things nice and safe when you use them. But that does get in the way of the compiler trying to optimize. So here's an example. If we wanted to make our add function nice and fast from the vector before, we can just inject a for loop that's nice and efficient. Not nice and efficient, nice and easy for the compiler to optimize. I've seen that a lot. It knows exactly how to play with that. So the important thing with this that maybe I think a lot of people have seen this function, but you can pass parameters into it, and that's what this syntax is. So we have a function that takes some arrays as raw pointers. By that I mean this literally just translates into float star. If it was when it passes C++, but it takes those and pops those references in there, and then you've got a nice vectorizable loop. So your code. So maybe you've done this, and maybe you run your code, and maybe it's not much faster, or it hasn't made a difference. We want to know if it's worked, so you can add the for different compilers have different flags, but you can pass some flags that will output a report on sort of line by line essentially, where it could vectorize, where it couldn't, why it couldn't, and so on. So that's super helpful for if you're trying to track down performance issues with your math libraries. My graphics programming, as I mentioned earlier, is my day job, and I have a love and hate relationship with it. GPU APIs are sort of they're monolithic and they're kind of ugly, and they're sort of not easy for beginners, which I think is a shame. I mean, from a low-level engineering perspective, they're great. They provide sort of an efficient hardware implementation. Efficient hardware-independent mechanism to control a GPU, which is fantastic. It's not easy to do that at all. But from the perspective of someone who wants to get into GPU, or maybe who just wants to sort of run a whole bunch of code at sort of massive parallel scale and do it really, really efficiently, it's not easy to get into because there's a lot to learn. So to sort of demonstrate what I mean, this is the WebGL API, and it's kind of it's huge. So it's just a big let's get on the screen. It's a big sort of stack of enums and functions, and I mean there's 140 functions and 237 enum values, and you just kind of have to read the documentation to figure out where which goes where, and you know how to use the functions. So it's kind of not user friendly. I mean the problem, and all these are in just some big global namespace, and it's a big sort of state machine. So it is sort of a nightmare to use sort of by hand, but manually. Yeah, and on top of that, I mean, because ideally when you're programming for the GPU, you've got some idea of something you want to run. You maybe want to draw an image, and you've got some program to color each pixel. You can't write that in the host language. So if you're writing Haxe, you can't write your shader in Haxe, or if you're writing it in C, you can't write your shader in C. It has to be written in some language that's specific to the API. In WebGL, it's GLSL, and it's like C-like language, and it's passed as a string. So it's a strangely messy process. So anyway, so how can Haxe make the ideal GPU API that other languages haven't been able to do? You can in fact write Haxe as a shader with Nicholas has written a shading language. I'll talk more about that in a second. But ideally, you don't want to be using multiple languages. You want to be able to write a program and have that run on GPU. And you sort of don't want this sort of separation between the GPU and GPU objects. Like if you have a texture, you want to be able to just access the texture width. You don't want to have to call a bunch of functions that will eventually return the width. So you want it sort of nice and simple, like you'd use any other sort of library. Obviously we want this for free, right? We don't want to have to pay for some nice abstraction. We want it to run as fast as possible. So using the features I mentioned earlier, like generic build macros and type-loading macros, you can pull this off. And this is what I'm very much interested in. There's a bunch of good libraries like Car's internal library and sort of SnowKit and a bunch of others that do make writing for the GPU a lot easier. The big one worth looking to is H3D by Nicholas, which has a shading language, say, written in Haxe, and it lets you it lets the compiler know about what's going on in your shader. So you can, if you can imagine, if before you have to write the shaders as strings, it means you can make a mistake in the way that your shader is connected to the rest of your code, and you wouldn't find out until the program ran. And look, if you can do it in the same language, it means the compiler will be able to catch errors like that, and a whole bunch of more useful things. So that's talk. Any questions?
Great, thank you. It's less of a question, more like a thought. It feels like when you use inline, it makes your code better. And according to your code, you use inline everywhere. Why would you suggest it's not a default behavior in the compiler?
Yeah. I see. It's there's a number of reasons when you wouldn't want to use it, and that you can. The problem is, if it's not code that's called really frequently, if it's code that's a function call isn't that bad. It's not super expensive. So if it's only if you've got some startup code that's a bunch of nested functions, it isn't. If you inline with it wouldn't really make a difference to the user. But the problem with inlining too much is you'll get sort of explosion lines of code where you've got a big function that includes some code, and that maybe includes another big function. You get this big chunk, and then maybe that function's called twice, so again that whole thing's duplicated. So you use it when you need it, but yeah, if you use too much, you'll blow up your code size. And most compilers like the JavaScript compiler and C++ compiler. They're all very good at inlining automatically anyway. So it's only in those cases where you want to really be sure it's inlining and not accidentally failing to write.
Thank you so much. Felipe, you ready?
Yeah, I can continue.
Yeah, I think it's very, very